You're familiar with the concept of a telescope. This is a collapsing telescope, right? It just all smushes together. You could do that with like a selfie stick too, like they all collapse down, right? Okay, so these telescoping series, these are so named so they are called telescoping series because their terms collapse into each other, onto each other. You will like these. Yes, ma'am. Okay. Our first example is a series that starts from 1 and goes to infinity of the terms 1 over n times n plus 1. And our directions are find the sum. Okay. Well, it's not geometric, so we can't do the nice little geometric term, but let's take a look at some of the terms. So we're just going to explore some of these terms. Okay, first term is, did I write this right? Nope, 0. Sorry, I wrote it. No. I was right the first time. You can't have 0. All right, first term. Okay, however, well, if we do that, we're not going to see the telescoping. Okay, next term. No, 1 over 2 times 3, which is 6. Next term, 1 over 3 times 4, 12. 1 over 4 times 5, 20. Okay, there's nothing really very interesting when that happens. There's nothing obvious. We can tell the pattern for sure, but it doesn't look like we can come up with an interesting sum. So we do a little algebra on this, and we go back to the original one, and we say, well, this looks like we could maybe break it up into partial fractions. Right? We have two things multiplied by each other. Okay, I'm going to save you the agony of the partial fractions. I worked it out already. I know you can do it. Okay. All right. And the partial fractions turn out to be 1 over n plus negative 1 over n plus 1. Now these two things are equal. We haven't done anything illegal. So let's see what the terms look like if we write them out as partial fractions. Okay, now, what's the first term? 1 and minus half. Plus, what is the next term? 1/2 minus 1/3. Okay, and what is the next term? 1/3 minus 1/4. Plus 1/4 minus 1/5, etc., etc., etc. Okay, until you get down to the last terms are 1 over n minus 1 over n plus 1, the general term at the end. Okay, so we notice if we rearrange our parentheses that this would look a little bit different. So if we started with 1 by itself, and then we put parentheses around the next two instead, so negative 1/2 plus 1/2. And then we put parentheses around the next two, which would be negative 1/3 plus 1/3, etc. Negative 1/4 plus 1/4, plus dot, dot, dot. Okay, we're going to end up with negative 1 over n plus 1 over n in parentheses, but negative 1 over n plus 1 left on the end without a parenthesis. So we have now left off the first term out of a parenthesis and left off the last term out of a parenthesis. So we see what happens is the collapsing of terms. Okay, all the parentheses collapse to a value of 0, leaving me with 1 minus 1 over n plus 1. So I want to take the limit of that as n goes out to infinity. Which is pretty obvious. When you plug infinity into there, we're going to get 1 minus 0 or 1. In other words, think back to the original terms. 1/2 plus 1/6 plus 1/12 plus 1/20 must also have the same sum, and that sum is 1. Okay, that is called a telescoping series. Do you feel like you want another example?
No.
At the end? I just took right here the general term. Okay, originally, right here, Megan, originally the 1 over n and the 1 over n minus n plus 1 were grouped together in a parenthesis. But I'm knowing that this one is actually going to get grouped in a parenthesis with the one before it, leaving the 1 over n plus negative 1 over n out at the end. Okay? I have another telescoping one ready, but I think that you probably get it. Okay? So let me show you the other thing. Okay, so that's the definition of a telescoping series. Okay, we have one more definition. And this is the definition of error. Okay, remember, this is going back a little bit to when we were doing Taylor and Maclaurin series. Okay, the longer the Taylor or Maclaurin polynomial, the more accurate it was. Okay, the less error. So the longer you extend the polynomial, your error will be minimal. Okay? So we assume our goal is to minimize error by extending a polynomial p order n as far as possible. But you got to stop somewhere. So wherever you stop, okay, well, that's order n. If we stop at, we say order 7, then we stop at 7. Okay, the definition of error. Whoops. Okay, the definition of error is the absolute value of the term that you cut off. Okay, if you cut off at P7, then the definition of error is the 8th term. Okay, we want to minimize that. We want that to be small. Because if we minimize the 8th term, then we know the 9th term is going to be smaller and the 10th term or whatever. But by definition, it is the next term. So it is the coefficient of the next term in the order, which would have come next, and then x minus a, where I have it centered, to the n plus 1 power. Now, do you remember how to find that coefficient?
Oh, it's the f, and then the n, and then x, the multiplier x, and then the factorial.
Okay. All right. So to find the coefficient, when we did Taylor, it is the prime to the n plus 1 divided by the factorial of n plus 1. That was how we created it. times x minus a to the n plus 1. Okay, that is the definition of error. It's the absolute value of the next term. Okay, so if you have that definition, then that allows you to solve this question, answer this question. Okay. What x values guarantee an error less than 5 times 10 to the negative fifth, so a very small number, for a second order equation which approximates, that was made to approximate the function ln of 1 plus x. All right. So we are going to the second order. So the definition of error would be the value of the third term, which is not included in the polynomial. The polynomial stops at the order 2. Yes, this is Maclaurin. That's a good question. Okay, great. All right, so our definition of error is the absolute value of, okay, well, what derivative do we need to use if we were going out to order 2? We need to order 3 derivative divided by 3 factorial times x minus a to the third. And we would like that to be less than 0.00005. Okay, I figured out the third derivative for us just to save time. The third derivative is 2 over 1 plus x cubed. I figured out 3 factorial to save us time. That's 6. And since this is Maclaurin, where is it centered? 0. And so this is just x cubed. And this has to be less than 0.00005. So let's clean this up just a tiny bit. So x cubed in the numerator and 3 1 plus x cubed in the denominator.
Oh,
You okay?
yeah.
Okay. Oh, I have my cube on the wrong. The cube should be outside the parenthesis. Because I was doing the derivative. Cubed. Okay, so we're going to use our calculator to solve that. If you take the absolute value bars away, you have negative 0.00005 is less than x cubed over 3 times 1 plus x quantity cubed, and that's less than 0.00005. 1, 2, 3, 4, 5. Okay, I solved this with my calculator. That means I made a tiny little graph. Okay, and the tiny little graph, oh, here, we're almost done. Tiny little graph had this little piece that kind of came through like this. And I said it has to be, here's the tiny little graph of 0.00005, and then here's the tiny little graph of negative 0.00005, and I used my calculator to solve that. So I got negative 0.0504 for the bottom one, and I got 0.561 for the top. Which one of those two numbers is smaller?
Wait. You mean 0.0.5?
No, 0.561. Okay, which of those, sorry, does it, oh, there, 0.561. Okay, which of those numbers is smaller? The negative one is smaller. We want to minimize. We want to make this interval as small as possible. So center the interval. So x must be between, so make it even smaller so that it's centered. All right, there you go. That's the x. Has to live in that interval in order for me to guarantee an error of no more than the original value that was set at the beginning. Because we want to shrink the interval to be as small as possible. The interval should be centered. Okay, it's got to be centered at 0. The interval should be centered, and we need it to be centered. You know, you can't make it centered to 0.561 because then you're going too far to the left. So you make it as small as possible.